problem, we are looking at an illustration of how an FPGA works, where we have CLBs, complex logic blocks. So you're seeing 3 of those here that are used and programmed to implement something like a state machine. So in this particular example, we have a really simple state machine that's just a counter. So we start in 0, 0, and when x is equal to a 1, we move to 0, 1. When x is equal to 1 again, we move to 1, 0, then 1, 1, and back to 0, 0. When x is 0, we just loop back to the original state. So on all x's that are equal 0, we loop back. All right, so a simple counter. All right, so what I want you to consider is the programming of the complex logic blocks. So the first thing that we need to take note of is that we've set this up already to where the intention is that Q2 is an output and Q1 is an output, with the implication being that Q2 should be going through a flip-flop. Now, that's the role of this particular box, or this programming connection, is to determine whether we connect to the D flip-flop or we don't if we just make this regular combinational logic. Okay, so the LUTs, to say that again, look up table logic here, implements combinational logic. This goes to a multiplexer. The multiplexer can either go to a flip-flop or it's routed this way. And so you have a choice by this programming box. Okay, so our first step is we would need these to be zeros so that the flip-flops are included in the circuit and Q2 gets connected through that flip-flop. This is another 0 where this is representing the flip-flop Q1. And then down here in the bottom complex logic block, we want to bypass the flip-flop. So we want to take that out of the circuit. So if we put a 1 there, then the output Z comes from the combinational logic from the 2 LUTs that are highlighted in green. Okay, so that's the first part. How do you program the outputs to set things up correctly? All right, the second part is how are we going to make these other programming connections that we see here for the yellow part, the purple part, and the green part. Okay, so to do that, the thing that we do is we need to look at the next state table. All right, so I've drawn the next state table already, and this is the format that makes most sense because I look at this and Q2 is controlling the multiplexer that feeds the inputs to the D flip-flops and the combinational logic for output Z. All right, so I have this set up to where I fill out this next state table and I can determine what the connection should be. All right, so let's go ahead and make that happen. All right, so the next state table is easy because this is just a counter. So on 0, 0, we stay at 0, 0. Okay, my screen's messed up, just a second. Okay, so in 0, 0, when x is equal to 0, we stay in 0, 0. All right, when we're in state 0, 0, when x is equal to 1, we count up. On x equals 0, in state 0, 1, we stay at 0, 1. On 0, 1, when x is equal to 1, we count up. On 1, 0, on a 0, we stay at 1, 0. 1, 0, on a 1, we count up. From 1, 1, on a 0, we stay in 1, 1. From 1, 1, on a 1, we loop back around to 0, 0. So those are the next states for the flip-flops. And the other thing we do is look at the output Z. The output Z always depends just on the state. So when we're in 0, 0, output Z is 0. When we're in 0, 1, output Z is 0. When we're in 1, 0, output 0, 0. And when we're in state 1, the output is a 1. All right, so that's the next state table. Okay, well, the way this is working is that when I look at Q2, all right, so Q2 is a 0 right here. All right, so I'm looking at the Q2 flip-flop. Basically, this is telling me the next state when Q2 is equal to a 0. All right, So I would literally just copy this over. When Q2 is equal to 0, we select the upper LUT, and this would be 0, 0, 0, 1. When Q2 is a 1, then we select the lower half of the LUT. Okay, and so that would program to 1, 1, 1, 0. All right, so then let's look at Q1. So Q2 is still controlling the mux for the purple highlighted LUTs. Okay, so we would look at this and let's choose the purple highlighter. When Q2 is a 0, we get this particular set of bits, and when Q2 is a 1, we get this particular set of bits. So we would then program the LUT to be 0, 1, 1, 0, and 0, 1, 1, 0. All right, and then lastly, the thing that we do for the output is, again, we look at how this is set up. Q2 is controlling things, so we look at Q2 when it's 0 and when it's 1. Okay, so we would get these two columns, so all zeros here, and 0, 0, 1, 1. All right, so this problem is good because it illustrates the idea of taking a state machine and mapping it as program connections into complex logic blocks that form an FPGA.